One thing that surprised me, and I had to learn somewhat late in my mathematical career, is that the solution to mathematical problems often goes through narrative, through storytelling. I thought that mathematics was a very impersonal subject where you just present equations and theorems and arguments without context. But actually, the context is very important. The key is often to tell a good story about it. Mathematical narratives take abstract mathematical problems and add real-world context. It can help you see that your goal is more than just solving for X. Making a problem fit into the context of a relatable story can also give you insight or clues about it. It helps the viewer understand what's going on if there is a protagonist, an antagonist, if there is some goal to solve, there's some obstacle. Framing things in a way which has a narrative to it, it activates certain parts of your brain. If you want to develop your skills to find analogies, to see connections, basically the most important thing is to ask questions. And the dumber the question, the better, really. So to give you one simple example from arithmetic, when you multiply two negative numbers together, let's say -3 and -4, you get a positive number, plus 12. But that's not very intuitive to many people. To many people, two negative numbers should combine to form another negative number. And so you can ask, is there some analogy you can use to pursue this? So you can maybe use an economic analogy. So if you want to multiply 3 times 4, you could say, okay, suppose I am being paid $3 an hour to do something, and you work for 4 hours. Okay, so every hour you get $3, and then after 4 hours you get $12. Fine. But now suppose instead of being paid $3 an hour, something is costing you $3 an hour. Maybe you're running water or something, or electricity, and it's costing you $3 an hour. So after 4 hours, this will cost you $12. So this is why -3 times 4 is -12. So you can ask, how can I push this analogy further? So then you can ask, how do you interpret -3 times -4? Well, suppose your water's running or something and it's costing you $3 an hour, but you managed to shut off the water for 4 hours. So you have saved 4 hours of expenses, and so you have saved $12. And this is why -3 times -4 is plus 12. So by exploring this analogy and just asking questions, well, what does this mean? What does this mean in this analogy? You can gain a sense of what multiplication of negative numbers really means. Your intuition is now better than it was before. It's actually very useful to anthropomorphize the mathematical objects you deal with. They're not just X's and Y's. Often you will hear, if you listen to a mathematician talk about a problem, they might say that this is the enemy, and certain things are good guys. Like maybe there's a certain powerful tool that we want to apply, but in order to apply it, certain conditions have to be met, and so you start working on that instead. If you want to solve for some unknown X, you could think of it as almost like a detective hunt or something. There's some mystery opponent who has, and you don't know the location of his opponent. He's located at X. And so you need to identify where X is. And this puts you in a mindset where you start thinking about clues. You can start using process of elimination. Okay, so X can't be this, because if X was equal to this, then this would happen, and this doesn't happen. So it can activate certain detective-type aspects of your thinking that help you realize how to solve your question. So I'm going to talk about an example of how you can use analogies or narrative to really understand a mathematical concept. So the example I'm going to use is that of polling. If you have a large population, such as the population of the United States, several hundred million people, and you want to know their position on some topic, like how many people are voting for a certain political party, we have these polls. And when you first learn about how polling works, it is unintuitive. A poll may only sample, say, 500 people out of 200 million possible respondents. And that's a tiny, tiny fraction of the whole population. But nevertheless, polls can be incredibly accurate. And one of the facts about polling is that the size of the population does not actually matter too much. What matters is the sample size. So a survey of 1,000 people will be more accurate than a survey of 500 people, regardless of what the total population size is. This is unintuitive, but a good analogy can really clarify the situation. So the analogy I like to use is, what is the salt content of the ocean. You can tell the ocean is salty just by taking a single drop of seawater, okay, and just tasting it. And immediately from one drop of seawater, you can tell instantly that the ocean is full of salt. And the reason for that is that the salt is quite well distributed within the ocean. Now, the beauty of this analogy is that it not only explains the initial question of why the size of the population is not so important, but it also tells you the limitations of poling. If the ocean contains freshwater portions and saltwater portions, if you sample the wrong portion, you can get a misleading idea of the salt content of the whole. And so sometimes polls fail because they are not polling a sufficiently mixed portion of the population. It's important to sample as randomly as possible. Try to poll people from different regions, different demographics, different social levels. If your population is 50-50 male and female, you should probably try to get a sample which is also 50-50 male and female. If not, you can correct for it with some math, but it will be more accurate if it's closer to the representative mix. Analogies are an excellent way of using both halves of your brain. The rational half, the formal half, which uses very precise, rigorous thinking, and the intuitive part, which is using analogies and intuition. Part of advanced mathematical training is learning how to somehow see a problem stereoscopically with both your rigorous perspective and your intuitive perspective, and to know how to translate back and forth. Going back and forth is actually one of the most fun parts of doing math, because you really feel smarter when you make the connection and you see how the numbers and the equations match with your intuition. Sometimes narratives can lead you astray. For instance, a lot of mathematics is centered around solving equations exactly, to the last decimal point. And it was only realized in the 20th century, really, that there are many questions, many practical questions where an exact solution is not possible. And what you really want is just an approximate solution. For example, Newton famously solved what's called the two-body problem in gravity, that if you have two massive bodies like the sun and the earth, you describe the orbits quite exactly. And people spend centuries trying to solve what's called the three-body problem. If you have three bodies like the earth, moon, and sun, what is the exact formula for their orbits? And no one could find an exact solution. In fact, we still do not have an exact solution for this problem. But that turns out not to be the right question to ask. The question to ask is can we compute the trajectories to sufficient accuracy for a sufficient period of time? Like if you want to send a rocket to the moon, it's okay to get within, half a meter or something of the correct position of the moon. Once you frame things in the context of finding approximate solutions rather than exact solutions, there are a whole different set of techniques that you can use. There's a whole different narrative. You can tolerate certain errors as long as they don't get out of control. And so it all becomes a question of controlling errors. For example, polling is another good example that, if you poll 1,000 people, there is a tiny, tiny chance that your poll will be completely off because all of the 1,000 people will be from a certain demographic, which has a bias. It's very unlikely, especially if you do enough randomization, but there is always a tiny chance of failure. But for many applications, it's okay to have a quick and cheap method that has a tiny chance of failure. Of course, like if you want to fly a plane, you want a near 100% chance that the plane will not fall apart. But if you just want to send an email from A to B, if it fails in delivery 1% of the time, that's not too bad. Knowing what error tolerance you have for your problem is important in finding the right framing. Okay, so what are the takeaways here? Firstly, framing a problem with a narrative or analogy can make a huge difference. Secondly, mathematics is not always black and white. Thirdly, a good narrative allows you to understand an abstract mathematical problem in a practical way. It can help you see the solution as more than just a numerical answer. A bad narrative, however, can make you think that you need a solution that's not actually necessary, such as a precise solution to a problem that might only require an approximate answer.